Okay, trophic ecology today. We left off last time talking about the studies in the Florida mangrove islets and the study by Simberloff and Wilson that followed taxonomic richness, species richness, over time on those defaunated islets. Another group of investigators came along and categorized the species that arrived on those islets by trophic type, or by foraging guild, loosely, the guild that those organisms belong to. So they took the same data and looked at it in light of trophic relationships rather than taxonomic assignments. Both are valid ways to approach the community in terms of its taxonomic composition or its trophic structure, but they're different ways of approaching the community. So we'll continue a little more with the discussion today of the trophic approach, looking at functional groups of organisms, and we'll get into food chains and the way food chains work, which sets us up for understanding the metabolism of a community, if you want, the basic energetics and mass flows in a community, which is really what ecosystem studies are all about in many cases. So this will be a bridge that we form to getting into food webs and ecosystems. Next lecture on ecosystem ecology. So we'll start with a trophic relationship, and I like carnivorans. Excuse me if you don't appreciate predator-prey dynamics of this nature as much as I do. We are going to look at a video, and you can watch it by clicking the button here if you're not here at lecture today. But it involves these European rabbits and these little ermines or stoats. A very small carnivoran, the little ermine, just a few hundred grams, maybe 400 or 500, not sure exactly. They vary a lot, males to females and across the time of the year, but it's little. It's a little weasel. And that's a big bunny, maybe 8 or 10 times the weight of the carnivore. So the dynamic here is interesting. I warn you, a rabbit does get harmed in the... Okay, that is not just gratuitous violence. It actually makes a point for us about the way mustelids, members of this family, and many carnivoran mammals, the way they overtake their prey and kill their prey is with their canine. And at the back of the neck, on the cervical vertebrae, especially for an animal that's much larger than itself like that, it's a killing bite at the back of the neck where a cervical vertebrae is crushed and the animal's killed. That's the foraging mode, one part of the foraging mode of an animal like this. Animals that forage for similar foods in similar ways are parts of a guild, are members of a guild by definition. A foraging guild, G-U-I-L-D, right? Borrowed from human society, the term. So that canine relates to the prey in size. Bigger the canine, the larger prey that can be overtaken. The larger the prey that can be overtaken. This is another weasel, closely related to the ermine, but it's even smaller. This thing's just 100 or 200 grams. Tiny, it's the smallest carnivore on Earth, the least weasel, tiny little thing. And it lives in Israel with martens on the same landscapes, so sympatrically on the same landscapes with martens. We have a type of marten here in California. This is another one. They are more arboreal than the least weasel, but also consumers of small vertebrates. There are also polecats in the system, genus Vormella. All of these living together. And outside of that family, another carnivoran, a mongoose, the Egyptian ichneumon. The European badger lives there as well, and your badger of YouTube fame, the honey badger. All of these guys live together, hunting prey, hunting vertebrate prey and mammalian prey, and overtaking them with the canines. Coexisting sympatric members of the same guild here. And what these authors did, and I believe Simberloff himself was included on this paper with Tamar Dayan and others, they looked at canine diameter in these species. So the diameter of the canines at the neck, where the gums are in the jaw, and they compared the species in terms of that diameter, and they found a stepwise relationship of non-overlapping values across species in this guild. Even more interesting than this apparent differentiation in size, which presumably reflects the differentiation in foraging strategy or types of prey taken, females to males within species themselves differed in canine size. So that step relationship in size differentiation across species was also reflected within species across sexes. That type of differentiation is what we would call the structure of this guild within this community. And there are other neat examples like that, particularly in the vertebrate world, with which I'm most familiar. These trophic categories, most broadly, are the familiar trophic levels of a community. And we've talked about this a bit already. Part of this is common parlance among the public. You're familiar with food chains. We grew up understanding something about food chains. The history of study of food chains goes back a long way, hundreds of years, thousands of years. There are recorded instances in the literature of people talking about food chains, if only poetically, with a primary producing level at the base. And most typically, these are the photoautotrophs receiving their energy from the sun, the herbivore level that eats the primary producers, or what's called the primary consumers, and then the secondary, tertiary, and quaternary consumers, and even higher if there are more levels in the chain. And this works in terrestrial environments and marine environments. You have a food chain trophic structure like this that you can tease out of any community. And it all starts with the primary production based on the sunlight or chemical energy at the base. Yeah, the history of food chains. I'll put a nice history of science paper up here that you can look at some of this history. It's really fascinating. Here's a food chain that was published in a paper in the 1800s with these organisms in a European lake. You have your microorganisms here, your phytoplankton taken by the zooplankton, taken by the small fish, which are taken by bigger fish, and then the fish-eating osprey on top in this system. A fish like this can eat these fish or can eat these fish. It's not just strict one-to-one up the chain. There are omnivores in these systems. In the terrestrial environment, you can think of omnivores as the consumers that are taking both autotrophs and heterotrophs. So the plant eaters, the ones that eat both plants and animals, like many of you. The most famous food chain in the literature is one from The Origin of Species. It was Darwin's, where he was basically relying on someone else's studies in outlining this, but based on some of his own observations in his own yard, noting that bumblebees pollinate clover, that field mice sometimes eat the bumblebees and their larvae, and cats feed on field mice. So if you take the cats out of the equation, the field mice are going to go crazy, the bumblebees are going to suffer, and the clover's not going to be pollinated. So built into the early concepts of the food chain is some aspect of causality and the effect of altering one of the levels in some fashion. Just spelled out there. So that type of causality is something that ecologists study a lot. It's of practical importance in the way we manipulate ecosystems or the way we've changed ecosystems, in looking at the effects that it's going to have in the long term or back on us. Bottom-up causality is intended in this direction, from the autotrophs up, indeed from the physical base, from the abiotic environment. If you have abiotic changes that influence the autotrophs, for example in nutrients or temperature or amount of solar energy available, insofar as it affects the autotrophs and then goes up the chain in its effects, it would be considered a bottom-up type of causality. Is there any type of top-down causality, where changes up here would influence changes below? Maybe it was in Darwin's early food chain, indeed. Although most studies have focused on the bottom-up perspective, the top-down perspective is quite real as well, and we'll look at an example of trophic cascades. We already have. What was one trophic cascade we already looked at? Killer whales, yeah, and sea otters. This is an example that illustrates an important point about, what do you know, big carnivorans again. This type of information is really interesting because of, similar to the killer whales, how an unassuming animal like this can have such big effects ecosystem-wide. Now, there have been some sightings recently. You guys probably get the warning emails from the university about these big cats. You guys get those, right? Yeah. There have been a couple sightings recently very near campus, or even on campus, of these cats. They're moving back into the area. Just a few decades ago, when Ronald Reagan was governor, there weren't many of these cats in the state. And when they received their protected status, they've been increasing in numbers. They appreciated the protection they were granted from hunting, for example, and they're doing pretty well. They're increasing in numbers. And they do really well in the East Bay, on the East Bay Peninsula. Why? It's one reason. Can you guess? Adequate resources. The deer. The deer do so well. The deer do really well in town. The cats are deer specialists. They're not people eaters. They're deer eaters. The attacks by these guys are really rare, extremely rare. And if they do attack, what do you do? Huh? Run like heck? Now, what do you do if they attack? What do you do if a mountain lion comes and gets you? Yes. Look very big like that. Wave your arms. Look big. Throw sticks at it. Yell. Fight back. By all means. If a mountain lion is actually in contact with you, fight back. They're actually very sensitive, shy cats. They don't want drama. And if you gouge the eyes and a few whacks on the face, and it will deter them. You really can overcome a mountain lion, even the smallest among you. It's true. Same with sharks, but particularly mountain lions. Lions are scary. Grizzly bears are scary. Mountain lions are, you can defend yourself. There are great cases of elderly being attacked and defending themselves. Really people more infirm than yourselves. So these guys are, they're coming back. There was one shot in downtown Berkeley just a couple years ago, right, at the old Elephant Pharmacy on Shattuck and Cedar. It was seen there in the middle of the night and ultimately was in people's backyards, and the police followed it for a couple of, an hour or more, and ultimately they shot it. The law enforcement here is not used to this problem, and they're not equipped or trained to deal with mountain lions, and it's going to become more and more real, as is the necessity of us as a culture to deal with this. We either shoot or we roll up our windows and admire the pretty kitty as it walks around. We have these sort of two modes of loving it or killing it, and we need an in-between, and that's where this whole concept of hazing these creatures comes in, to develop a relationship where the cats understand that they are welcome and safe in the parks, but less welcome and less safe in town, and a way that we can also avoid just shooting them. Anyway, their ecological importance is very real, of these cougars or pumas or mountain lions or catamounts or whatever you call them. That's all the same name for this. It's all different names for the same cat. Here in Zion National Park, where the cougars are rare, well, where people are present over the last many decades, cougars are rare. So the areas of the park where people frequent, the mountain lions don't go there. And where the cougars are rare, well, you don't find cougar poo. The cougar scat is minimal, and it's abundant where the cougars are common. Where the cougar are rare, the deer prints, the tracks of the deer, are noticeable and abundant. All these things are measured quantitatively by the investigators in this study. Where the deer are abundant, the cottonwood trees fail to recruit and grow. The cottonwood trees being one of these trees that's common along riparian corridors, or along these wetland corridors, along rivers and streams, and they just don't grow up. They fail to grow up because the deer browse them down so efficiently. And when the cottonwoods are browsed down, it has an impact on the other vegetation and indeed on the geology of those stream and riverbanks, such that stream erosion is high when cottonwoods are low in numbers. And this has happened over decades. These kinds of broad ecosystem relationships don't happen overnight. The mountain lions started to become rare there in the 1920s, 1930s, and these are the types of effects you can see today. And that has effects not only on the plants and the geology, but it affects, in particular, amphibians, frogs and toads and things are much more abundant, and that's been quantitatively shown, where mountain lions are common. More mountain lions, more frogs. What do you know? It's an unexpected sort of connection. And by any measure, a healthier habitat here. So the impact of taking these big carnivores out of the system is only now being realized. Similar examples have been found with wolves, but then you look across the whole world, and modifications in the top predators that have occurred over the hundreds of years, thousands of years, millions of years that has occurred, but particularly with the introduction of guns and movement of Europeans around the world. These are real broad ecosystem changes that are resulting. And this is new. This is a pretty new understanding of those connections. This is a way to show how bottom-up forces can influence community structure. The trophic cascade is a nice example of a top-down example. I'll use this as an example of bottom-up. It also is a test of the so-called energetic hypothesis for how the number of trophic links in a community is influenced. One of the ideas of why trophic chains tend not to be very long. They tend to be 3, 4, or 5 steps and not much longer. Why aren't they longer? Well, there are several hypotheses for why they're not longer. One of the best supported is the energetic hypothesis based on how much energy is available to the system in relation to, well, what we'll see, the inefficiency of energetic transfer across levels. Here's a study on tree holes. Trees commonly form these cavities within their trunks, and those are ecosystems in their own right, in these tree holes that have their own communities of organisms within them. What these guys did was manipulate how much food went into the tree hole, because the community in there, mostly microorganisms and arthropods, the community feeds on stuff that falls in allochthonous input, stuff from the outside. Don't worry about the term, but allochthonous input is material that comes from outside the system, and that's what drives that system. Litter, detritus that falls in. On natural levels of food input, detrital input, at natural levels of litter fall rates, you have typically this many species in that little community, this many trophic links on average, connecting the members of that community. Well, what these guys did was reduce by 2 orders of magnitude the amount of litter that went into the tree hole and monitor the effect on species richness and trophic links, and found that the less material allowed into the system, the fewer species and the fewer trophic links within the community. And for them, it supported the energetic hypothesis that the more energy allowed into the system, the more complex the community, the greater number of links, the greater number of species. That would be a bottom-up sequence, right? Because the litter itself is your food, the base of your chain. So with those sorts of connections across the community, we can speak of a community metabolism. I'm going to give you a few diagrams here because sometimes seeing more than one diagram of the same phenomenon can help you understand it. All of them have their flaws. An example like this starts with the sun and the solar energy. So your energetic connections in red, and these can be chemical energy. Here you have radiant solar energy coming in and being captured by the primary producers, and that chemical energy that they capture and store in their biological structure is taken up by the herbivores, and it enters the detrital, the very important detrital category, when these things die and are decomposed. Mass is represented by the blue, and one thing we notice with the energy in the system is it ultimately flows out of the system. Much is lost as heat during respiration, during biological respiration, as the primary producers capture the energy and assimilate it, and as it's transferred to the herbivores, cellular respiration leads to the loss of energy as heat at each level. And the heat in the detrital, wow, I don't know how I did that. The heat in the detrital component also ultimately leaves as heat. And it's for that reason that we speak of energy as flowing through a system. Energy flows, whereas mass cycles. Mass ultimately doesn't leave the global ecosystem, except in some rare cases. For example, if you send a satellite into space, yeah, you're getting out of the Earth's atmosphere and sending mass into orbit. That's not even necessarily leaving the Earth forever, because it may very well re-enter the atmosphere. That's a minor point. The point is that mass cycles within the biosphere, and energy flows out, because that energy lost to heat this can't be recovered by the biota. It's lost from the system. Mass cycles within the system, but it may be lost from the local system. It may flow downstream and get into another community, another ecosystem. So it may be lost locally, but globally it would be cycled, unlike the energy. A real example from a famous study in Florida at a nice place called Silver Springs, a spring-fed wetland. This is from the original paper. Cracked me up when I saw these two fun young students sampling the ecosystem. They're both holding turtles that are good herbivores in the system. It looks like a lot of fun to be doing ecosystem studies in this Florida spring, at least to me. And here are some real data from that system that put numbers in calories to show how much sunlight you begin with, how much is captured by the producers in the gross production of the autotroph level, how much is lost to respiration, how much is then just subtracting how much is lost to respiration from how much is captured, gives you how much is available to the next level, the net production. Of that net production, much of it will just either flow downstream or die in decay. So what gets transferred across levels is even less than how much was net produced. So just a small amount that reaches the next level exists relative to the first level. That trophic efficiency is actually really low. And it's even lower at the higher levels because these organisms in their metabolism tend to be less efficient than these organisms with their different metabolisms. So you can check those numbers, and I urge you to put some percentages on the diagram. See about how much in percent are moved across these different levels. Another way of viewing this, again, we're talking about community metabolism. We're starting with the sun. Here we are in estimating the amount of energy from the sun in kilocalories per square meter per year. So how much solar input there is in a square meter over the course of the year. Well, less than 1% of that energy that strikes this ecosystem surface is captured in gross primary production. Most of it will just be radiated back, not captured in photosynthesis. Of the amount that is captured, of the amount of gross primary productivity, the amount captured by the primary producers, most of it, at least half of it, according to this diagram, is lost as heat. What isn't lost as heat is called the net primary productivity of the system. And that's the energy that would be available to the primary consumers once you subtract the detrital flow to that all-important category of decomposers, detritivores. And you can follow that down the line. And this gives it in relative scale to show just how much is actually ingested by tertiary consumers relative to the original input. It's a small fraction because of these losses as heat and these losses to other pools. That's the efficiency with which these systems operate. Another diagram. It's just another view. Really represents the same thing. Gross, loss as respiration,